And this is the second part in this practice exam solutions for the Calculus and Vectors course. So I just finished the first part, so if you want to look at the detailed solutions for the multiple choice, that's also available. And so in part 2, the first of the questions where you have to show some work, you're given these two vectors p and u and asked to find the angle between those two vectors. We use the dot product, the rearranged dot product, to find that. So the cosine of that angle is the dot product divided by the product of the two magnitudes. And so in order to find this angle, then we need the dot product of two vectors. So the dot product of these would be, we go 3 times -2 plus -1 times 5 plus 4 times 1, which works out to -7. We also need the length or magnitude of the two vectors. So the magnitude of p be the root of 3 squared plus -1 squared plus 4 squared, which works out to the root of 26. And similar with u, the root of -2 squared plus 5 squared plus 1 squared works out to the root of 30. And so substituting -7 in here in the numerator and the root of 26 times the root of 30 in the denominator, 26 times 30 is 780. So take the -7 divided by the square root of 780, you get this decimal approximately -0.2506. And so to find the angle, we take the inverse cosine of that. So the inverse cosine of this is about 104.5 degrees. So that's the angle between those two vectors if they're placed tail to tail or tip to tip. For number 2 here, we have monster truck alpha pulls on an object with a force of 12,000 newtons at a direction of north 15 degrees east. So this would be the 12,000 newtons right here, north 15 degrees east, so this is a 15-degree angle. Monster truck beta pulls on the same object with a force of 15,000 newtons, east 5 degrees south. So this would be straight east, so 5 degrees toward the south would be this vector right here. So this is the 15,000 side in the diagram. And those are the two sides in the diagram. Now, we're asked to find at what direction and with what force should monster truck gamma pull in the object so that the three are in a state of equilibrium. Nobody's going anywhere. So we really need to find the resultant of these two, and then the monster truck gamma has to pull exactly opposite to that vector. So you could use components. I've used some trigonometry here to find the resultant of these two vectors. So this side would be 15,000. If this side is 12,000, then so is this side over here. And so in this triangle, I know two sides, and I can figure out the angle between them. So if that's 15 degrees, if I draw a straight up north line from the end of this 15,000 vector, then this would also be 15 degrees here. In this little right triangle right here, if this is 5 degrees, then this is 85 right here, between this vector and the north-south line that I drew. Because remember, three angles in a triangle have to add to 180, and if one of them is 90, that means the other two have to add to 90. So that's why I know if this is 5, this is 85 here. So this whole angle right here would be 85 to there, plus another 15, which makes 100. So that's why this angle here is 100 degrees. And so I can use the cosine law to find the length of F, which represents the resultant of those two forces. And so the magnitude of F would be 12,000 squared plus 15,000 squared minus 2 times 12 and 15,000 multiplied times the cosine of 100. So if you do all that, take the square root. Remember the caution here, if the angle is over 100, the cosine's negative. And so be careful with your signs, because this negative times another negative here will actually end up being a plus whatever this works out to be. So be careful with your signs there. You should get, after you take the root, 20,733 newtons. So the magnitude of monster truck gamma's vector would be the same, 20,773 newtons. But of course, we have to calculate the direction, because if that truck does not pull in the right direction, it's not going to be in a state of equilibrium. So in order to find a direction, I'm going to find the angle between the 15,000 side and the resultant of here. So this angle is my theta. And so I'm going to use the sine law to find that. The sine of that angle over the 12,000 side here would equal the sine of the 100 over the resultant, the 20,773. And so if we multiply 12,000 by the sine of 100 and divide by 2773, and then take the inverse or arc sine of that, we'll get sine theta is 0.5689. So that's the sine of the angle. If you take the inverse sine of that, you get 35 degrees. So this whole angle from here down to here is 35. Now, remember this little bit right in here is 5. So the angle that F makes with the east line would be 30 degrees, because 35 minus that 5 is 30. So that's 30 degrees. And so for my equilibrium, and I'm going to make a couple drawings here. So if this line goes straight east-west, that's actually going towards the west there. If this angle right here is 30 degrees, then this angle right here would have to be 30 degrees. And so the monster truck gamma should pull with this force at a direction of west 30 degrees south. See, that would be west, and but it's going 30 degrees toward the south. So that's the vector that gamma has to pull along to make everything in a state of equilibrium. On to question 3. It says, use a diagram to draw 2a minus 3b plus c. So I've made some drawings here. In order to draw 2a minus 3b plus c, so 2a mean we want two of these vector a's. So we would start like this. There's an a, and there's another a, so that's 2a along here. And then minus 3b. So this is vector b right here, so we actually want the opposite of this vector. So I'd have to take this vector and draw it in the opposite direction. So here's my negative b's. So I would put a negative b there. I want 3 of them all together. And another negative b there. And another negative b here. And then I want to add vector c. So here's my c here. And so there's my c vector. And so the 2a minus 3b plus c vector is the one that goes from the beginning of the first 2a vector to the end of the last c vector that I put there. And so that's why that blue vector would be 2a minus 3b plus c. In number 4, it says, prove that a dot b equals b dot a algebraically in 3 space. So this is a Cartesian proof. We're going to use Cartesian vectors for this. So I'm going to call a the vector a1, a2, a3, and b the vector b1, b2, b3, where the a1 to a3 and b1 to b3 numbers could be any real numbers whatsoever. That's why this is a proof and not just a demonstration using specific vectors. So a dot b, we'll figure out what a dot b is and b dot a and show that they're the same. That's how the proof basically works. So a dot b is this vector dot this vector. And so to take the dot product of them, I would go the x component times the x component plus the y component times the y component plus the z component times the z component. So it's that's what a dot b is. To do b dot a, it's just the two vectors in the opposite order dotted. And so we put b first and a second. So we go b1 times a1 plus b2 times a2 plus b3 times a3. Now, because the a1s and a2s and a3s and b1, b2, b3, etc. are real numbers, then b1, a1 is the same as a1, b1. And B2, A2 is the same as A2, B2, and we can also switch B3, A3 and equals A3, B3. And of course, that in mathematics, that law is called the commutative law, that B1, A1 is the same as A1, B1, or 3 times 2 is the same as 2 times 3. And so because we can change that around, that this ends up being exactly the same thing we got for A dot B over here. So that proves that A dot B is equal to B dot A in 3-dimensional space for any vectors in 3 space. For number 5 here, it says find a vector perpendicular to B and C. And so the cross product gives you a vector perpendicular to the two. Now this is just one of many ways you can do the cross product. So if I'm taking the cross product of these, the way this method works is you start with the y components. You go y and then z, and then cycle back to the x and then write another y again. Same with the c vector. So I start with 4 and then 2, and then back to the -1, and then the y component again. So we go 7 times 2 is 14 minus the product of 4 and -3. So actually minus 4 times -3 would be the same as plus 12. And then -3 times -1 is that 3. Minus 2 times 2 is 4, so minus 4. And then 2 times 4 is 8. Minus -7 would be plus 7. And so that works out to 26, -1, 15 for B cross C. In number 6, it says describe the difference between the geometric and algebraic representation of a vector. Well, the geometric means to draw something. It uses a directed line segment looks like this. So that's a geometric representation for a vector. It's a drawn vector or array. Array is the same as a directed line segment. While the algebraic representation uses numbers that are distances horizontally or vertically. So for example, 26, negative 1, 15 is an algebraic representation for a vector because it means to start at the origin, go 26 in the direction of the x, 1 in the direction of the negative y, and then 15 in the direction of the positive z. So algebraic uses numbers. So that's the difference between the two. For number 7, it says find parametric and symmetric equations for the line through the point 705 and negative 243. So we need first, well, we don't have to do it first, I suppose, but we need a direction vector between the 2 points. And so we subtract them. It doesn't really matter whether you go, the tail is here or the head is here. You have to go between the 2 vectors in some fashion. So I'm using the 705 as the head of the vector because I'm going 7 minus negative 2, and then 0 minus 4, and then 5 take away 3. And so that works out to 9, negative 4, 2. Now if you subtract in the opposite order, you would get negative 9, positive 4, negative 2, and that's okay. There's nothing wrong with that. So to write the parametric equations, here's 2 ways you could write them. The 9, negative 4, 2 are the coefficients of the t or the s or whatever you use for your parameter. And the beginning goes the coordinates from one of the points. So 7, 0, 5, so 7 at the beginning here, 0 here, and 5 here. Or if you want to use this point, you could put negative 2, 4, and 3 at the beginning of each. And so that's 2 different ways to write the parametric equations. The symmetric equations, I wrote the symmetric equations for each of these. So it would be x minus 7, y minus 0, such as y, and then z minus 5. It's x, y, z minus each of these numbers on top. And what goes in the denominators are the numbers from the direction vector, the 9, negative 4, 2. So same idea here. This one comes from these parametric equations or this point. So y minus negative 2 is same as, x minus negative 2 is the same as x plus 2. Y minus 4 on top here, z minus 3 on top here. And again, we put the 9, negative 4, 2 direction numbers in the denominators. So that's another way to write the symmetric equations. For number 8 on page 6, says find vector and Cartesian equations for the plane through these 3 points. Now, so this is the equation of a plane. In order to get the vector, you need 2 vector equation. You need 2 vectors in the plane, 2 non-parallel vectors. So we could take vectors between any pairs of these points. So for example, I use these 2 to find my first direction. It's not really a direction vector. I called it D1, but it's a vector in the plane, parallel plane. So I went 8 minus 11, negative 4 minus negative 2, and 1 minus 3. And so negative 3, negative 2, negative 2 is a vector in the plane. And then I also used the second and the third one to find a vector between those 2. So I went 6 minus 8 here, 1 minus negative 4, same as 1 plus 4, and 5 take away 1 would be 4. So negative 2, 5, 4 is another vector in the plane. And so there's my 2 vectors in the plane. So to write the vector equation, it's x, y, z, or some people write r here, equals. And you take, at the beginning, is the position vector of a specific point in the plane. I used 11, negative 2, 3. You could have put 8, negative 4, 1, or 6, 1, 5 here. It wouldn't matter. But plus t times one of the vectors in the plane plus s times another vector in the plane. So that's a vector equation. One of many possible ones. Now, to get the Cartesian equation, you need the plane kind of looks like this. So let's say that's the plane, and let's say this is the D1 vector, and this is the D2 vector. So there's the 2 vectors in the plane. In order to get the normal to the plane, you need a vector perpendicular to both of those. So that's why we use cross product to find that normal vector will be the cross product of these 2, or a normal vector would be the cross product of those 2. So that's why I take the cross product of D1 and D2 to get that normal vector. And so similar to the previous question, this is the way I do cross product of these 2. I got 2, 16, negative 19. So that's the coefficient of x, y, and z in my Cartesian equation. So that's why it's 2x plus 16y minus 19z plus some number d equals 0. The way we find the d is you substitute in one of the points. And I used 11, negative 2, 3. If you wanted to use 8, negative 4, 1, that would work just as well. And so putting the 11, negative 2, 3 in here, you get D is 67. And I did want to demonstrate that if you use a different point, you do get the same D value here. So this is if we used 8, negative 4, 1 instead, and you do get 67 again. So, and of course, if you use the 615, it'd be the same thing. So that's the constant at the end of the equation. The 67 goes here. So 2x plus 16y minus 19z plus 67 equals 0 is a Cartesian equation of this plane. And number 9 asks to describe all the ways a line and a plane may exist in three-dimensional space and the types of intersections they may or may not have. So a line and a plane. So the yellow thing with the or reddish border is the plane. So the line could intersect in a unique point. So there's the point of intersection right there. And so the line and the plane would have a single point of intersection. The line could lie on the plane like this. And so every single point that's on the line would also be on the plane. That line is said to be coincident. So there's an infinite number of solutions here. The last way is that the line could lie off the plane but parallel to the plane. And so it doesn't matter how far you go in each direction on the line, it's still the same distance above or below the plane. In space above and below don't really have a significance, but the line would never touch the plane, so in that case they would have no solutions. In question number 10, you're asked to find the intersection of these three planes, and if it happens to be infinite, also find a particular solution. So that means just an example of a specific point that happens to be on all of the planes. And again, make sure you describe the type of solution. Now, so these are the three planes. I'm going to use elimination here. And so what I'm going to do first of all is I'm noticing that the three z's are the same. And so I'm thinking if I subtract them, then I can eliminate the z's right away. And then notice I brought the 8 and the 4 over here. And so if I subtract these, and actually the x's are the same too. So if I subtract them, I'll get 3y take away negative 1y, same as 3y plus y. So that's 4y. And it would equal 8 minus 4 is 4. And so y works out to be 1. And so it kind of looks like there might be a unique solution here because y is 1, but that doesn't actually mean it has to be. So we just know that y is 1. So I'm going to, so I'm going to try to eliminate z again, but with a different pair of equations. So I'm noticing that this 6z is double the 3z. So I could take that first plane and multiply it by 2, and that's what I've done here. And then this is the third plane here. And so notice when you do multiply them like that, you actually get the same plane. So the first plane and the third plane are actually the same plane. So subtracting them gives you 0 equals 0, which implies there's an infinite number of solutions. So the infinite number of solutions means that we don't have a unique point. But there is, the only way that the three planes can exist so they have an infinite number of solutions is if they're coincident, or so because there's an infinite number of solutions, we'd know that these three planes would have to intersect in a line. And so I'm going to take the first plane's equation and let z equal t, and then also substitute the 1 because I know y equals 1 in place of y. And so this would become 3t here. I brought the 8 over, and then 3 times 1 is 3. And so bringing the 3 over and subtracting the 8, I get 5. And of course, this becomes minus 3t over here on the right side. So x equals 5 minus 3t is the parametric equation for x. Y is 1. And z is t. So that's the line of intersection of these three planes. To find a particular solution, take a number and put in place of t. So I use 1. So I put 1 in here. So 5 minus 3 times 1 is 2. And so 2, 1, 1 is an example of a point that is on all of the three planes. For question number 11, so The average rate of change, I made a drawing here to assist this explanation. The average rate of change is the rate of change over some horizontal distance or a period of time between 2 points. So between 2 different points as opposed to a tangent line that just touches the curve at one place. It is defined as the amount of vertical change, the dependent variable, which would be this amount right here, or the delta y, or the rise, by the horizontal change. The horizontal change is this distance here. By the way, this and this are the 2 points that I'm referring to. For example, the average speed of an object between 2 seconds, so let's say this was 2 seconds and 5 seconds. So those values right there would be the displacements, and this would be the change in time between the 2 seconds and 3 seconds, for example. So average rate of change is between 2 different places on a curve.